Since the dawn of time, man has compiled code. Ancient compilers were given to us by Mother Nature. Man tried his hand at this divine creation and barely made it out alive. Now, it's my turn to make one. Hey fellas, I invented my own programming language and made a compiler for it. It can do advanced programs such as adding two numbers together. I had a couple rules for this project. AI cannot write code for me, it must be written myself. The compiler also had to be decent. No shortcuts, no cheating. Do it all from scratch. I wanted to be a purist and chose to write it in C. I had almost zero real experience with C, so it was the obvious choice. Let's get started. The first thing to do was create my own programming language. People don't usually think about this, but syntax is not the only thing that sets languages apart. They usually follow a design paradigm that sets them apart from other languages. For example, Rust's paradigm is memory safety. It is difficult to allow faulty memory access or usage. Or, in Java, the paradigm was write once, run anywhere, using the JVM to compile portable bytecode. After some thought, I decided on a small subset of C. Each interesting feature scales up development time by a large margin, so I wanted to keep things simple at the beginning. Here are 3 example programs in my language. I'll walk through how these get transformed by the compiler into machine code. Now, what really is a compiler? Well, the file a programmer writes is just a long string, and the goal is to transform it into machine code. The first step in this process is to lex, or tokenize the programmer's input file. Well, actually, I need to get the file open first. I struggled to get started since I hadn't written much C code before, especially on a big project. After some messing around, I made a simple input argument parser, just to find the file path written and write it into a buffer. Now I was ready to lex the file. Just kidding, I did actually write an argument parser and a function to write it into a buffer. Now, lexing. It's actually pretty straightforward. You just store the type of word you see, as well as which line and column it's on. Each token gets split into a keyword, an identifier, or a delimiter. These are the only types of objects that can exist during lexing. I also had to make a mini vector implementation to store the token's data. In case you didn't know, a vector in C++ is actually just an array, but it's dynamically sized. You set a default size, add elements until it's full, and if a new one needs to be added, you allocate a new array with double the size, copy the old elements, and add the new one. So, my token buffer is essentially a C++ vector. I was slowly starting to wish I had some nicer data structures, as C doesn't give any. Keep this in mind, it's important later. So, we have a buffer of tokens. What should we do with them? Well, now's the fun part, parsing our tokens. But first, I want to tell you guys about an interesting decision I had to make. Most of the data you deal with in a compiler is dynamic. The compiler doesn't know how big the program is or what's actually inside it. So when we store information about the program tokens, syntax nodes, symbols, it usually ends up being dynamically allocated, just like with the token buffer. The traditional way to do this is calling malloc for every piece of data, and then later calling free on each one individually. It works, but it's kind of a mess. Instead of allocating memory one object at a time, you allocate a big chunk up front and then manually place objects inside that region. If the region fills up, you just allocate another block and keep going. Once you're done, freeing memory is trivial. You free the entire arena at once. I was intrigued, but not sure if it was necessary. But up to this point, things were running smoothly, and the whole point of this project was to learn, so I figured, why not? So I decided to implement my own arena allocator. It wasn't that easy. This was my first introduction to messing directly with memory in C. Debugging the arena was difficult, and you have to worry about the memory alignment of whatever you're storing, which was some interesting math. After some struggling, I got it up and running. Even though it was hard, knowing what I know now, this was the best decision I made in the whole project. Made my life so much easier not worrying about freeing memory. Just one free at the end of the program and bam, memory handled. Now, we have a nice setup for parsing tokens. Why do we need to parse tokens at all? What should they turn into? The meaning of a program is inherently recursive. To know what an if statement does, we need to know its body. To know how an expression binds, we need to know an operator's binding power. This is why the smartest idea is to turn the tokens into an abstract syntax tree, or AST. To create the AST, we have a main recursive loop that looks at the current token, and sometimes looks ahead when the current token is ambiguous. Then, just call parse object for whatever object we saw. The most interesting parsing example is expressions. Arithmetic expressions are not as straightforward to parse, so we use a technique called Pratt parsing. Let's walk through an example. There are 3 operator types: prefix, infix, and postfix. This example only has infix, so that's what we'll focus on. The basic idea is we need to find an operator's binding power. When we see an operator, we need to decide, does the expression we've built so far become the left-hand side of this operator, or do we keep parsing and let a stronger operator to the right take it? To determine this, we parse expressions until the next operator is too weak to bind at the current level. Let's try it out. When we start, our minimum operator binding power is 0, since we haven't seen any yet. I'll keep a reference here to binding power. The numbers are arbitrary, just the relative order matters. First, we see 1. Let's assign that as our initial left-hand side. Then, we advance the cursor and see plus. This has a power of 1, as shown in our chart. Since this is higher than the minimum power we're currently allowed to consume, we need to recurse to find the rest of the expression. Inside that recursive call, we start the loop again. We see 2, and treat it as the new left-hand side. Then, we advance and see multiply. This has a power of 2, which is higher than our current binding power of 1, so we recurse again. Now, we see 3. This becomes the left-hand side for this level, but there are no more operators left to advance to, so the loop ends and we return 3 to the caller. Back in the previous level, we take that result and assign it as the right-hand side for our multiplication. This forms the subtree 2 times 3. Now, this level is also done, so it returns that entire subtree back to the first call. Finally, we assign that result as the right-hand side for our addition. Our left-hand side was 1, our right-hand side is the expression 2 times 3, and we're done. This is the core of Pratt parsing. If we see an operator with a higher binding power than our current level, we recurse. This automatically ensures that higher precedence operations are tucked deeper into the tree, so they happen first during evaluation. Phew! That was the most difficult part, which culminated into this! The rest of parsing isn't too difficult. Like I said before, the rest of parsing is just recursive calls to build an AST, nothing crazy. With parsing finished, I really started to feel the pain of C. I needed some kind of diagnostics tool in case the programmer writes faulty code, so I had to implement yet another mini vector to handle diagnostics, but it was only usable in the parsing stage, not the rest of the code base. I was really wishing I had some nicer features other languages might have given me. I really wanted this compiler to be decent, so I wrote my own error struct. It basically implemented its own vector that stored error strings and had pretty printers to show line and column numbers as well. The plan was to use it for the rest of the compiler if anything went wrong. With that out of the way, we can move on to the next stage of compiling. In essence, we can group most of the stages that happen in the pipeline as semantic passes. They handle things like checking if the types assigned to a variable are correct, or if a function with a returned value always returns on all paths, or promoting compatible types if necessary. I won't go into too much detail about these, but I'll talk about the two passes that my compiler actually had: scope and symbol resolution, and definite assignment analysis. Depending on the compiler, some passes are unnecessary, but scope resolution is required. It does two things. It links all common symbols to one object, and it enforces proper variable scoping. We store symbols we find in a table, keyed by the name of the symbol. For declaration statements, we add a new symbol entry to our table. For assignment statements, on both the left and right hand sides, we ensure that the symbols already exist, and then we store which symbol object it is inside the node. Scope resolution goes hand in hand with creating and finding symbols. If our program has more than one scope, such as one created by an if statement, we are allowed to call variables by the same name, and the compiler knows it's okay because the names are constrained to the if statement scope. So, we hold a scope stack. When we see a new scope, we push it onto the stack, and any symbol names we come across get pushed onto this level of the stack. If we see a name that we can't find in the current stack's level, we go to the previous level to search for it, all the way to the root scope. And that's scope analysis. Next, I had a definite assignment pass. The purpose of this is to ensure that a variable is defined before its use, since in max minus minus, you can declare integers without defining them. I actually ran into big problems with this one. When I first made the pass, I didn't have any if or while statements, so doing a linear check of uses and definitions was fine. But what happens in this case? We don't know if x is assigned here because it depends on the value of y, so we need some notion of what's called a control flow. I was too lazy to deal with this, and I left my definite assignment as a linear scan. It was better than nothing. Next is the final stage of the front end, and it's something that I think is really interesting. Let's take a look at something that's called an intermediate representation, or IR. Most modern compilers use one. The goal is to help with portability of a compiler. It's easier to turn some intermediate language into different assembly architectures rather than directly translating the programming language. There are two main types of IR, stack-based and 3-address codes. There are pros and cons to both. The JVM uses a stack-based IR, but I ultimately chose a 3-address code mostly because they were more familiar to me. In more advanced compilers like LLVM, they use a form called SSA, or Static Single Assignment, where every temporary can only be assigned once. I kept things a bit simpler, but the spirit is the same. I invented my own IR, which I called max minus minus IR, or MIR. It has a pretty minimal instruction set that allows full expressiveness of the language itself. The basic structure is this. We start by declaring functions. Each function declaration is represented as a collection of blocks. The reason for blocks is for portions of code that require control flow. The scope defined by an if statement requires a different block. The blocks construct a control flow graph, which depicts all possible scopes that the program might take during its execution. Then, each block holds a series of instructions. Each block requires a terminator, so it knows which block needs to execute next. The instructions use temporaries, which are analogous to registers in a real architecture. The main difference is that we can assign infinitely many temporaries, while real architectures have a finite amount of registers. One small thing to mention, I chose a code that depicts variable addresses as stack slots, so when we see slot X, that means the address containing the value of X. Lots of interesting things happen during IR generation, so I'll only focus on a couple of them. First, how can we ensure that expressions get evaluated in the proper order that we built in our AST? The solution is to use a stack to hold the temporary values we generate. We traverse the expression tree in post order, which means we visit the left subtree, then right, then the operator. In MIR, calculations are always performed using temporaries. If the value used in an operation is a variable, we first load it into a temporary. If the value is an integer literal, we use that directly. First, the visitor goes left and sees X. we generate an instruction to load x into a new temporary t0 and push t0 onto the stack. Now, let's move to the right subtree. We see the value y, and similarly, we emit a load operation, generate t1, and push t1 onto the stack. Now, we visit the right side and see 3. Literals don't need to be stored in a temp, so we just push 3 onto the stack directly. Next, we visit the multiplication node. The operator pops the 2 latest values we saw, generates the operations instruction, and pushes the generated temporary's value, t2, onto the stack. Finally, we return to the root addition node. It finds exactly what it needs waiting on the stack. The multiplication result t2 is on top, and the original t0 is right below it. It pops them, emits the final add instruction, and pushes t3. A lot of instruction emission is mechanical, but there are a lot of special cases. Another interesting one is any statement that creates a scope, such as if or while statements. An if-else statement branches execution into 3 new blocks from the current one. Our cursor starts out pointing at the current block. We create 3 new blocks, then, else, and join. It becomes a matter of moving our cursor to the proper block, emitting all instructions in that block, then moving the cursor to the next. The result is a control flow graph that looks like this. While statements end up creating 4 blocks, where one is created only to check if the condition remains true. I'll cover one more cool concept in my compiler, which is called short-circuiting. When you write a condition using AND, if the first part is false, the second part doesn't even need to run. In my IR, I handle this by constructing the blocks so that a false on the first check jumps straight to the end, skipping the second check entirely. The same logic applies to OR. If the first part is true, we just skip the rest. It's a tiny optimization that prevents unnecessary work at runtime. There are more interesting concepts in IR generation. There's something called desugaring, which is lowering one piece of code into another, such as transforming a for loop into a while loop. I didn't happen to need this for my compiler because there are no for loops. This was most of IR generation. The ideas weren't too complicated, but implementing them properly, especially with strange recursion rules, gave me a headache. I really struggled to get this working when I first did it. Oh, and remember how I said I wished I had nicer data structures? Well, all of functions, blocks, and instructions are dynamically sized depending on the program size, so I needed yet another vector to hold all of these. It was at this point I threw my hands in the air and just made my own generic vector that I could use for everything. It just stores a void pointer that can be cast to any struct. I also made a hash map because I knew I'd need it later. But man, the relief I felt when I ran the code and it showed the IR I invented was amazing. I finally felt like the compiler was getting somewhere. I mean, I'm basically there, right? This looks very similar to real machine code. I'm nearly done, right? Right? Yeah, I wasn't even close. I had no idea what I was getting myself into. Once I found out what other compilers' backends look like, I was crushed. Let me tell you guys my journey of making a compiler's backend. I was annoyed and unmotivated, so I tried to find the path of least resistance and take any shortcuts I could. I get to work, and eventually get to a stage called register allocation. I knew what was involved, and knew it was a nightmare. I just wanted to see some compiled code, so I skipped it entirely and did a linear mapping between my virtual registers and physical registers. I was also fighting C really hard. So many dynamic allocations, using vectors everywhere, and weird nested dynamic structures. I tried to store data in a minimal way so I wouldn't have to invent more data structures. After lots of work, I got to assembly emission. I compiled my program and it worked. It created assembly that compiled into a program. I was ecstatic. This program actually worked, and nothing I do usually works. I wanted to try a more difficult program and immediately ran into a problem. I didn't have enough registers. Even something extremely simple ends up using more than 7 registers, which is all I had. At this point, I took a step back. I heard of a magical language called C++ that would solve all the problems I was having in C. I was seriously considering rewriting the entire backend in C++ and actually taking my time so each stage was done right. After some deliberation, I chose to rewrite everything in C++. I was unhappy with the work I did and wanted the compiler to be robust even if it was for a simple language. First, I'll talk about the typical idea of a compiler backend, then what I chose to do. The goal is to convert our high-level IR with no hardware constraints into actual assembly. We need to fit the puzzle of the machine architecture, whichever it is. I chose to compile down to ARM because x86 has a lot of strange backwards compatibility rules and difficult instructions. ARM is much more straightforward. Most passes here can be split into either optimizations or changing an aspect of the IR to fit a real architecture. The front-end IR prioritizes correctness and canonical form. The back-end focuses on making it efficient. Even though optimizations are very interesting, I was still more focused on getting things working, so my compiler does not have any optimization passes. Let's walk through my pipeline. First, I was highly recommended by my mentor to make an IR verification pass to ensure the IR follows the rules I created for it, such as ensuring loads only load into a slot, checking temps are only defined once, checking that temps used are defined earlier, or ensuring all blocks end with terminators. It helps pin down bugs and ensure nothing in the front end did any incorrect work. Next in my pipeline is a lowering pass. The IR gets lowered into another IR, but this time it closely follows the rules that the architecture requires for instructions to be generated. We'll call this new IR lowered IR or LIR. It's roughly at this point that my pipeline starts becoming more architecture specific. For example, in ARM, the store instruction cannot store an integer literal or immediate. So when we see this instruction, it has to generate a new one above the store that first materializes the immediate into a virtual register, and then stores the value in that register. There are other niche rules where immediates must be materialized, such as during a return instruction. The goal isn't necessarily to turn the IR into perfect assembly, but rather to make assembly emission easier. Another interesting change is how operands are modified to fit operation instructions. The right-hand side of an add or subtraction instruction can only stay as an immediate if it fits certain constraints. Otherwise, it also gets materialized. However, the destination and the first operand must always be registers. Only the second operand can be an immediate. There are many other techniques one can use to generate more optimized instructions, but this covered what I was willing to deal with. I want to stress that my backend is extremely simplified, and a real compiler's backend has many more passes and optimizations than mine does. Real compilers often have multiple lowering stages of the initial IR. Now, let's talk about my favorite part of this entire project, the register allocation pass. Our LIR has infinite virtual registers, but ARM has 31 architectural registers. Far fewer are freely allocatable. I'll give you a quick crash course on ARM register conventions. But first, in case you don't know, local variables during a function's execution are often stored in a region of memory called the stack. The stack is used to hold data whose lifetime is limited to the function call. So, in my IR, a variable like slot x is assigned a spot here in memory. Now, there's a register called SP, or the stack pointer, which just points to the current top of the stack. x29 is called the frame pointer. It's a stable reference point in the stack, since the stack pointer might move during a function's execution. X30 is called a link register. It holds the memory address where the function should jump back to when it finishes. X0 to X7 is used to pass function arguments. X0 is also used to return a value from a function call. X9 to X15 are scratch registers and can be used for anything. I'm going to ignore X8, X16, X17, and X18. They are used for complex linking and OS-specific features that we don't need here. X19 to X28 are a bit more nuanced. They're preserved registers. When a function gets called, the previously mentioned registers can be overwritten. We have no guarantee about their state after exiting the function call. They could be completely different. But these registers come with a guarantee. Their values must be identical after a function call. So when we return from the callee, we know they will hold the same values as they did before. So let's say we have this set of instructions. We see that this register is used both before the call as well as after. Since we need to ensure its existence after the call, let's store it at X19. That way, we know we have the value we need when we return from the callee. But here, this value dies before it gets to the caller. We don't care about what value it had, so we can store it in X9 and the callee can do whatever it wants to X9. So how can we determine whether a value can be stored in this section or this one? Before allocating registers, we'll need to do something called liveness analysis. We need to determine how long a virtual register lives for. A value becomes live after its first definition and is killed right after its last use. We scan backwards because liveness depends on future uses. A value is only live if it will be used later. We build each interval for each register we come across. Now we know which registers can be stored in Scratch versus preserved, but we have another problem. Even though we know these registers are Scratch registers, there's too many of them. We have a lot of virtual registers, but only 7 Scratch registers. Now we'll need to somehow map these into real registers, but also make sure no values that are needed at the same time overlap. But wait, we know how long each variable is live for. Perfect! We can use this information to allocate registers. There are different allocation algorithms, but I chose to implement one named linear scan register allocation. It's fast, but not the most efficient one. Another one exists named graph coloring. It's extremely interesting, but vastly more complicated to implement, and I was trying to speed up development time. The core idea of linear scan is actually quite simple. When we encounter a new interval, just greedily assign it to any currently free physical register. We iterate over a list of our intervals, sorted by start time. To make it work, we keep a list of active intervals. Before we assign our register, we first check our active list to see if any intervals already ended. Here, no active intervals have ended, so we move on. Then we can just greedily assign that interval to an available register, and set that register as filled. Now, at our next interval, we do the same thing. Check if any active intervals ended. Now, V1 has finished, so we can set that register as available. Again, we just assign the interval to the first available register. At the next interval, V2 hasn't finished yet, so we'll have to assign V3 to the next register. But when we reach V4, V2 has finished, so we set that register as available, and assign V4 to it. We continue in this fashion for the remainder of the registers. In this case, we only needed 2 registers. Cool. But what happens if we need more registers than are available? If it happens that all registers are full when we try to assign, we'll have to spill that value, meaning we'll generate a new stack slot and store that value in memory instead of in a register. I know that was a handful, but it's a powerful tool and compilers wouldn't work without it. It was the most fun I had in the whole compiler. All that work, just for a small mapping list. Neat, huh? Well, what's next? Luckily, not too much. Remember how I mentioned the stack in memory? The next phase is assigning our stack slots to concrete stack offsets. Real stacks grow downwards, so I'll flip this to match reality. In ARM, the stack pointer must stay 16 byte aligned, so the total frame size is rounded up to a multiple of 16. We just take each of our slots from our IR, as well as any generated slots from register allocation, and assign them a position on the stack. The typical convention is the old link register, the old frame pointer, all callee saved registers, and then all local stack slots. Now, we're ready. We're one step away. Time to actually emit assembly code. This part is mostly mechanical with some nuance. Most instructions are a one-to-one mapping, which makes this part pretty simple. The only real concern is our stack slots. Each function gets its own stack. Within each function, there's sections named the prologue and epilogue. The purpose of the prologue is to save the old link register and frame pointer of the caller function, move our stack pointer, and save each callee saved register we're going to use. So let's say function A calls function B. Function B's prologue executes. B knows that it uses x19 and x20, so regardless of what's in there, it will save those values to the stack in the prologue, execute, then restore those values in the epilogue, which is just the reverse of the prologue. Each function is self-contained. It only cares about what it is doing, not any previous or nested calls. For each function, we just emit its label, emit the prologue, emit all instructions, then emit the epilogue. We use our mapping from register allocation to convert virtual registers to real ones. We've done it. We converted this input program into assembly. Let's try it out. This program should just add x and y in a function and print the result. There we go. Pretty anticlimactic for all the work we put in, just to print one number, and such a simple program too. But there it is. So, that's my compiler. I wanted to give you all a basic idea of how your programs get executed on a machine. If there's one thing I learned from this project, it's that a real compiler is not a one-man job. Even something this simple took me a month of steady grinding, but it was a really fun learning experience. I wanted to add cool features to make the language unique, but even simple features like more types or arrays introduce their own can of worms. Dynamic allocations are even crazier to implement. I saw what was involved and chose to pause the project here. Maybe one day I'll come back to it. I caution anyone who wants to make their own from scratch like I did. It's a great way to learn, but a ton of effort to do it right. By the way, you can check out the project on my GitHub, link in the description. If you use the -d flag, you'll see every step of the process yourself. I hope you all learned something, and thanks for watching.